All right, ladies and gentlemen, welcome to the 36th running of the APEC Micromouse Contest. So this is the 40th running of APEC, but we missed a few. We only started in the second year, so we weren't there for the first one, and we took 3 years off during the pandemic. So one of those they canceled on us, one of them was virtual, and one of them was sort of touchy-feely, so they just didn't know whether they wanted to take the risk of having a Micromouse. But we're back again. We have a good group. Tonight we have 17 entries, so this is actually a lot for us. We'll see how we do. And so the first person that's going to run is Harjeet with Zeetah VI. So let me explain the contest to you while he's running. So the goal is to build a robot that can find its way through the maze. It always starts in one corner and it's trying to get to the middle. When the scoring system starts, then we'll all breathe a sigh of relief. So the first part of the run is usually a search phase. It doesn't know how to get to the middle. So it knows that it needs to get to the middle, but it doesn't know where the walls are. Usually they run at a slightly reduced speed during this period of time. They're searching, they're looking where the openings are, okay? And they'll map out some sort of a path to the middle. Now at that point, they need to get back to the start square. There's a bonus if you don't touch the mouse. So you'd prefer it to never be touched, which means that it has to sort of go back to the beginning. It makes sense to search on the way back. So you search in and you search out. Now at this point, you may have seen all the best paths, and you may know that you're done. But you may also say, well, you know, there's a part of the maze that I haven't seen yet, so I'd like to see that. And so then you have to decide whether you want to search that now, or whether you just want to go back to the beginning and go in. So now he's had to touch it because it crashed. It probably remembers most everything that it's learned so far. So if you don't touch it, you get 2-second benefit, okay? But once you've touched it, then it doesn't matter if you touch it again. So you lose your 2-second benefit, okay? So in addition to the time of your run, we also add 1/30th of the total time that you've spent on the maze. So this makes it a little bit complicated, but the scoring system takes care of it. But the idea is that we're trying to encourage efficient searching. And it's boring when the mice search and search and search. So we're trying to make the contest fun to watch. And so we have a penalty on that. So we don't want you to over-search. Now, this was a problem, more of a problem early on when the mice didn't go so fast. Today they can generally search most everything quickly. So now this one may have finished learning, and it knows that it's already been touched. And so there's no good reason for it to run back to the beginning. You could pick it up, you could usually get there sooner if you just pick it up. But the other advantage is you can clean the tires. So cleanliness is everything. Traction is really important. So it's figured out which run it likes, and so it's now going to go in on that run. So usually the first time in, you try to be a little bit mellow so that you have a high probability of succeeding, and then you tend to increase the performance. Usually the performance is divided into different things. How hard you want to accelerate on the straights, how hard you want to brake, what kind of maximum velocity. The chance of crashing is quite a bit higher when you're going really, really fast. So you might limit the velocity on a straight. And then what kind of lateral acceleration you want around the turns. So how fast you want to go around turns.
Yeah, I think it's missing out the wall, so not like this.
Yeah. So it keeps crashing in the same place, right? So probably it has a mistake there. Right? So now there's a question, right? You have one more run.
It's not going to do a fast run, we'll just relearn. So.
Right, okay. So, thank you, Harjeet. So this mouse will talk to you, and this is supposed to be something that I can use to help you hear it. Wait. The voice is supposed to sound like HAL 2000. So I think it does actually myself. The robot is blaming it on human error. So the mouse has decided that the maze is unsolvable, right? So presumably it put in a wall that it shouldn't have.
You are destroying my mind.
You had to reset it, so it said, "You're destroying my mind."
Most reliable computer.
So you get 5 tries for each contestant, and you get the total of 7 minutes. So when this contest first started, you got 10 tries and 15 minutes. So it took a while. But today they run fast, so it's not necessary to take so long. So just before it crashed, it said, "If you check my service record, you'll see that it's completely without error." Bang. You've added a few more voice messages since last year.
I went a bit mad with it.
You went crazy.
It knows it's one trajectory optimized. Move away from the centre then. And by any practical definition of the words. Another dead end.
They've got one more run.
Hopefully it's remembered that.
It's remembered a lot of what it's learned.
Condition red. This phase is outside.
Oh well. Well, thank you, Hal. Okay, our next entry is M-Force. If any of the kids want to come up close, they're certainly welcome. And people are standing at the back, but you can come up if you'd like. And certainly if you're little, you're more than welcome. All right. So these people have come all the way from Portland, Oregon. This is our farthest contestant. Oh no, we have people from Japan, sorry. and the UK. Anyway, farthest from the US. So when you first build one of these, it's easiest if you just go ahead one square, and you run your maze solver while you're not doing anything else, and then you can go ahead another square. So you see that kind of behavior here, that it stops for every square. After a while, you can overlap your action, so you never stop or you go faster. Still usually keep the velocity down. You basically have to be prepared to stop within a square, because that's about how far you can see ahead. So you pick a speed that you'll be able to stop that way. Yeah, I think LiDAR would be allowed. At the other end of the spectrum, sometimes people use ultrasonic, but sound is really slow. So, and it's kind of echoey, and so you have to wait a long time for the echoes to go away. Has been used. There's one entry here that actually has ultrasonic on the front. All right, it made the corner. So by far, the hardest part of this challenge is navigation. So, getting your sensors, first of all, they don't always give you the right answer, and then secondly, you usually don't make exactly the right correction, in terms of what you want to do, and then the motors and tires don't always do exactly what you ask for. So in that sort of slippery environment, you're trying to keep it all together. When I first built a mouse, I sort of took the attitude, I'm in the wrong place. If I had a wall on the left, I didn't need to look on the right. I could just look on one sensor and it would give me all the information I needed. So that turned out to always be a big mistake. So it's much better to look at all the information that you have. If you have walls on both sides, you should average the result. If you're going by an open wall, you expect the opening to happen at a certain time, right? And so you could mark that down, but then maybe you'll see another opening, and so you should average those two. And so trying to add all of the data together turned out to be very, very important. All right, well, thank you very much. Okay, we have our first international contestant from Japan, our first Japanese contestant. So, Al was from the UK. Go ahead. Yeah. So from the Tokyo University of Science. So this entry is using stepper motors. So you might be able to hear them buzzing. When the contest first started, it was very common to do that. One of the nice things that we like about this one is that light sensors are using red LEDs, so you can actually see where they look. So Harjeet suggested that I place this entry after the people that were in the conference got here so they could actually see this one running. So I think we haven't fully done that, but we're close. It's always nice to know what it's thinking. So you notice when it hits a dead end that it turns around and it backs into the back wall. So that's to sort of recalibrate its position. Very well. All right. Yay! Well done. So it made it to the middle without being touched, so that's good, right? And now we're going to finish the circuit. And the business about going into a sidewall, right? Turning 90 degrees and then backing into a sidewall allows you to correct in both dimensions, right? Your side-to-side error and your front-to-back error. So you can fix both of those with these kind of actions. So there's no rule about hitting the wall. There is a rule about you're not allowed to knock down the walls, right? So we try very hard to make sure that the walls stay in place. And the mice don't push that hard, so it's not usually a problem. A really dramatic crash by a really heavy mouse will probably break a wall or a post. Occasionally that happens. Not so often as it used to. Oh no, I think she might have turned it off. All right. So the first run was 67 seconds approximately, and this one is 57, right? So it took about 10 seconds off. The run itself was 48 seconds, so it's a little bit faster, but it had some maze penalty time, and it was touched. Oh, not the first time, but the second. So there are different strategies, and oftentimes you search in, then you search out, and then maybe you make a speed run with what you know. And then on the way back, you could do a few more searches if there's other things that you still don't know. So typically, you mark your walls as either open, closed, or unknown. And so then you can make assumptions about the unknown walls and figure out what kind of solution that would be. Thank you. So if you look up there, you can see that the last run, the fifth run and the third run were about the same length, but the score for the last run, 61 seconds, and the previous one was 57. Okay, so her best score for today was 57 seconds, so that's great. And I'm glad it was successful. When you come halfway around the world and your mouse crashes out, it's always dim. So I've been there, and I appreciate that. Thank you very much. Okay. Matthias? Here we go. So I'm going to tell the story while you start, right? So Matthias was a student at Case Western Reserve, and he worked on a Micromouse when he was there, okay? So he's not a student anymore, he's working, but he showed up this morning and asked if he could try one of his mice. And so this is it. So here we go. So I thought that was impressive. Right around at first bend. It's outstanding. So for 35 out of the 36 contests, the same person has designed the mazes for the APEC contest. So his name is Gerardo Molina. He worked for me as a student, but he was also on our first Micromouse team. So in 1986, we made our first mouse. It was a bunch of people from the lab. Gerardo was in charge of the maze design, but we were using an 8051 processor, so that's where his experience was. But since then, he hasn't been involved in building the mice anymore, and we don't use his maze solver anymore. So it's legitimate to have him design the mazes because it's not code that he wrote that's actually solving them. So today, he actually has a new solver that he made that can solve diagonals as well as straights, and he uses that when he's doing the maze designs. Now, when you're trying to design a maze, obviously there's a range of people that are going to be participating in this contest. So if you make the maze really short, then the really fast mice, the times are so short that it's hard to tell them apart. And if you make the maze really long, then it's really hard. All right, well, thank you. Okay, flip-flop. And we haven't seen it yet, but there will be mice that can do some of these fancier shapes, like the diagonals. And so those things are hard for the beginning mice, but they also demonstrate what the better mice can do. So they often end up here. Do you want to say anything before you run?
This is the first robot from the University of North Carolina, Chapel Hill, and we designed this in a month.
All right.
Yeah. We're off. Oh, no. Yeah, sure. So having facilities to test the mouse is often a problem. This maze doesn't look that big in this room, but when it's in your living room, it's... So, a lot of people have never seen a full-size maze until they come to their first contest. So to get around that problem, the Japanese came up with a half-size mouse contest. So everything is half-size. The walls, instead of being spaced 18 centimeters, are only 9. They're half as high, they're half as wide. Yeah. And so for many of the contests, they still run a 16 by 16, and so the thing is a quarter of the size. But for the final contest in Japan, they actually run 32 by 32. So it's a massive amount of searching. Sometimes they get tired and they just block off a section of it when they make the pattern. But it makes for super impressive. And you have to be really good at building things if you're going to build one that fits in such a small space. But today, they basically run as fast as the full-sized ones, maybe faster. So it's very impressive. Okay, well, thank you. Thank you for coming. All right, excellent. Okay, let's see, who do we have next? Biscuit. So was it January or December 17th that you started? December 17th. So this one, he started working on it on December 17th. This is amazing to me. And if you come up afterwards and look at it, the build quality is outstanding. So it's really impressive. The trouble is with the mice today is that they are super low. So I see people standing, right? So thank goodness we have the overhead view. And it's actually worse with the half-size mice. All weekend. So this is very satisfying. 29 seconds, a little bit, and the score was 33. So this will be a typical strategy then. He thinks that he's got the best score that he can get, so now he wants to get the best time he can get, so he's going to clean the tires. So I think I told you before, cleanliness is next to godliness with the Micromouse. It's totally true. Before the contest, after we set this up, we used lint removers to take all the lint off the track. We used to use vacuum cleaners, but the lint removers work much better, so we're really happy with that. And the Japanese have ones that are just the right width for the track and have a nice long handle, so you don't have to lean over too far. So it's really quite convenient. So these long straights are quite difficult because you don't have good information about where you are as you're going. And you typically are going very fast, and so you don't really know until you get to the end whether you're in the right place. And then it often turns out that as you accelerate, you're not as far as you think you are because your tires are slipping. But as you brake, then you're going further than you think again because your tires are slipping. So if you don't get any information on the straight all the way down, you actually come out well. But if you're halfway down and there's an opening, then you can use that to correct your position. But you corrected it when you weren't where you thought you were, right? And then during the braking, you're going to skid. So it's difficult. Okay, and so, the previous run had a time of 29 seconds, and that one was 25. So he took quite a bit of time off of his run, so that was great, The strategy was well done. Thank you very much. Congratulations. Okay, Pico Classic 4. So Yuki is the friend of everyone that competes in the Japanese Micromouse Contest that comes from overseas. She always welcomes us, and she's on the committee, and so she helps us out. So she owns a robotics company, and one of their products is making mice. And so these are kit mice, often that other people use to begin with. And so I think this is one of her latest kits. Then her next entry that she's going to show is her private entry. It's not a company entry, but this is sort of the company entry. She works on behalf of Micromouse around the world, so we appreciate her efforts. And we really appreciate that she comes here. So you can see here's another entry that uses the red LED, so you can see how the sensors are doing. And realistically, the difference in intensity between red and infrared is not that big. So you could use red without a problem. seconds for the time, the run time, and about 37.5 for the score. So it still hasn't been touched, so this is great. So you can see that strategy that I talked about before. She searched, she ran in on a speed run and then she's searching on the way back. About 27 seconds. Yeah. So the previous speed run was 33, so significant improvement. Oh, okay, so the next run is going to try to do diagonal, so we'll look for that. All right. Oh, another choice. Whoa, baby. So she has one more run, so she does have an opportunity if she wants to clean the tires. Try it again. Oh. All right. Well, thank you very much. That was great. Okay, NanoXRP. There you are. All right, Jacob. You want to say anything? You don't have to.
I started working on this 2 weeks ago, and I'm just very excited to be here. So we're going to do our best, folks.
The real reason Jacob is here was to encourage FIRST robotics teams to come to APEC. And so that's what his original plan was. And I thought while he's here, he would also try to make an entry and run it. I'm covering you while you're getting started. But it turns out the FIRST robotics contest is in 6 days. So nobody that's working on FIRST right now wants to do a PR event at APEC. That gets tired. That may work with FIRST robots, but it doesn't work with Micromouse.
Okay, that's gonna be it for me.
All right, thank you. Next year, Jacob, next year. Okay, our next entry is Mongrel. From UC Irvine. Okay. Oh dear. All right, well, thank you so much. Sorry about that. Okay, Pedro. Pedro comes to us from Puerto Rico. This is our first Puerto Rican entry, so we're very excited. All right. Okay. So the very first Micromouse Contest, 1979, New York City, the entrance, well, the goal was where it is today, but the entrance is where it is today, but the goal was also on an edge. So it turns out if you have the entrance and the exit on an edge, you can always build a wall follower that will be able to get through the maze. And so this was a contest specifically designed for the microprocessor, which was brand new at the time. But it turned out it was won by an entry that had no microprocessor at all. It was just a wall follower. It was a motor, an arm, a switch, and a battery. Right? So everybody was depressed that their new contest was a catastrophe, right? But a clever guy in England realized if we put the goal in the middle and we put open walls around it, wall followers will never get to there. And so that's what they did. So today we don't always worry about having an open ring around the goal, but you could if you were worried about it. Wall followers generally aren't in the mix these days. But this one seems like it would like to be in that world. That's right.
Yeah, probably switch the battery. That's allowed.
You can do it. Okay. All right, thank you very much. Okay, we have one more entry from Yuki. Yes. Oh, okay. So she completed it 5 days ago. This morning, apparently, it was the first time she was trying it here. It has a Japanese and American flag on it. Yeah. Not happy here.
Thank you so much.
All right. It's good to have a goal, and it's good to have a contest to sort of get it ready, right? So basically, she's built it, right? So now she's ready to do the software the next time, so that's great. All right, the next one is Peter Harrison. Do you need help? So there's a club in the UK called UK Mars. They don't. What does UK Mars stand for?
United Kingdom Micromouse Robotics.
Okay, United Kingdom Micromouse and Robotics Society. And so they support Micromouse in the UK. And since I'm a member, it's an international club. But in any case, they have developed different kits, and they work on mazes and things so that they can make it easier for people to enter into the sport. And so the base for this is one of those kits. And then it's also the base for some software that Peter is trying to make public, and so this is an opportunity to get it all debugged and to test it out. And then later in the contest, he'll be running another entry, which is sort of his private entry.
Children disappointed. So decided to do another search, even though
for the entries fast enough to do a search again. So.
See, there's a square there.
Since it's already been touched, right, there's no penalty to clean the tires. And for many people, it's actually easier to have it come back to the beginning because they have a hard time reaching across the whole maze, so they make it come back anyway. Depends on how tall you are.
How many years you've Okay, everybody, make a prediction. You're
All right. Well, that's too bad. All right, thank you, Peter. The next entry is from Japan. They have many contests in Japan. A series of student contests, a series of anyone contests. He is the winner of the student contest in Japan, which was held this year, I think, just before Christmas. So we are pleased to have him come here and participate here for us. The student contest was in December, and then the overall contest was in March. No, it was in February, I think. Yeah, February, sorry. 7.6 seconds on the run. A score of 11.4, more or less. So you probably heard it. There was a fan on it that's used to suck air from underneath the vehicle to create downforce. And so that's why it has such fantastic performance. All right, 7 seconds. So the power of the fan, is significant, so you don't want to run it too much, right? Something that's really quite clever is the kind of skirt that they make to go around the outside to seal the air intake. So that has a lot to do with how well this works. It needs to seal well, but also needs to be not too sticky, to be slippery, so that because it's sliding around the ground. When you go this far, you'd like to have a good run, so I think you should be pretty happy. Okay, Mr. Fusion. All right, well done. Derek and Jim work together on the Micromouse and generally make a video about it, and so eventually that'll become available in public. So it's a video about our contest, so it's usually quite cool. They've integrated diagonals, right, during the searching. eventually lose it. Huh? So when Derek and Jim arrived in the States this time, they were busy rebuilding their motors. So the brushes started to fail. So a lot of these things are glued together, so they don't come apart very well. So it's impressive that it's running, frankly, that they took it so far apart and it's still doing well. You never know what spares to pack, but motors is not usually one of them. All right, great, thank you. You shaved 20 thousandths off. Good job. Cute. All right. Thanks, Derek. Okay. So I talked about the half-size contest. So this entry is actually made for the Japanese half-size contest. Normally, when you run one of those in a full-size maze, the walls are far away, and so the sensors don't always do so well. So it's impressive that this one works so well with in a full-size maze. And it's nice to have an entry that can work in any contest, basically around the world. People don't build them anymore, or as a rule, but you know, four-wheel drive and four-wheel steering were possible entries that people made in the past, and there were even half-size versions of all of those things. So it's amazing how good they can be. He's starting it over. Yeah, front. You think you missed the front wall somewhere? Yeah, okay, I agree. Whenever they hit the wall, then you always wonder, right, whether they understood it or not. And then if you recover, there's always a question of, well, should you throw out some of the last things that you learned because they may be mistaken if it crashes and then you pick it up. You'd like to not search from scratch, but you don't know exactly what to do. No problem. The fan. That's super impressive. Okay, it's going to go for more speed. So there are encoders on the wheel, so they often use those to input information. So he's pushing buttons and then he's turning the wheel a little bit to put it to the next level, whatever that is. So there's many, many ways that people do this. You even need little tools to clean the tires at the half size wise, right? Everything is tiny. All right. Well, thank you very much. All right, we got one more entry. Ish.
So I've been doing this for quite a while. The nerves never go away.
Since he's had good runs, I can tell his tail. So early this afternoon, he was testing, and some father asked me, "Do the mice ever come off the track?" And I said, "Nah." But I had actually seen his go 3 feet high in the air. Right? And it turned out he chipped a tooth on the pinion for one of the motors. So he took it apart, and he realized that was only chipped on one end. And so if he turned the pinion around, then he would still have enough teeth to engage. And he put it back together, and he was too afraid to test it anymore. And so it's great that the thing is working. All right. Whoa, 7.2. No, you need 200 more milliseconds. 7.013, and you're at 7.191. I mean, approximately. These are engineering things, right? We are into milliseconds, so that's honorable.
Okay, so what you need now is positive thought.
And we got 2 runs.
2 runs.
Oh no, run, I'm sorry.
This is
One.
it, all or nothing, right?
All or nothing.
Fingers crossed.
We need to get ready to match.
Oh, don't.
I don't know.
Don't do that. Well, the speed above this one is the one that launched it into the air. I'm not going to go there.
Give us a second. I think we know which is the fastest run, but we have a few other prizes to give out.
Well, it's almost over.
All right, give the help, Archie. Appreciate it. All right, thank you, everybody. Thanks for staying. I hope you enjoyed it.